All right, what's up? Today we'll be doing the interference question. I have made a worksheet for you covering all the content here to do with interference. Go through this in a second. We'll be dealing with slit interference and also diffraction gratings, and finally polarization. I'll go through the theory in a minute, but here's the exam questions organized for you in this worksheet. It's quite a lot. It's 50 pages long, as you can see, and then all of my written answers and links for both of them will be in the description. Let's talk about interference. Okay, so there's basically three equations you need to recall and understand. That is the slit equation, which is this, the diffraction grating equation, which is this, and finally, I don't know how to say this name, but Müller's law, which is to do with polarization and relating intensities. So let's talk about it. Okay, so interference. What is interference? This is the superposition, which we talked about. Make sure you've watched the first waves question video before this. Superposition of two or more waves from a coherent source. Coherent meaning things with a constant phase difference. We can basically have constructive or destructive interference. Constructive is when they arrive at a point in phase and thus add up. Principle of superposition, add up their displacements. And destructive is when they're completely out of phase and thus completely cancel out. You have a diagram here which can show you that. See, this red line is the resultant line of these two waves interfering. So this one, B, would be destructive interference, and this would be constructive interference, right? Because the waves are adding up here and they're canceling out here. That's important with interference because when we're looking at interference patterns, we'll have maximum points of amplitude when two waves are interfering. This is constructive interference, and when there's no light or a resultant displacement seen, and that's when we have constructive interference. So when we're looking at interfering sources, it's important to understand this idea of path difference. It's basically the path difference, so the extra distance traveled by one wave compared to another, and depending on the path difference between the two sources of the waves, will give us constructive or destructive interference. So, if we have these two wave sources and they're producing coherent sources of waves, well, their path difference will give constructive interference or destructive interference. And so when they're in phase, basically, they'll have a 0 degrees, they will be completely in phase, 0 degrees, 360 degrees. They're completely in phase. Well, this happens when the path difference between the sources, between the two waves, is n lambda, 0 lambda, 2 lambda, 3 lambda, right? Which makes sense because one wavelength, well, even if they're out of phase, I guess, by one whole wavelength, or they have a path difference of one whole wavelength, well, they're still going to be constructively interfering perfectly. And for destructive, well, this happens at the half wavelength points. Path difference, because at that point where they'll be out of phase by 180 degrees, or integers of 180 degrees, or 1.5, so 180, 540, this kind of thing, because at half a wavelength point of difference they are destructively interfering, and that's important. So we need to look at the path difference between two waves when they're coming together, or if their path difference is half 1.5, 2.5 wavelengths, well, then they're destructively interfering. And if they're 1, 0, 1 wavelengths, 2 wavelengths, 3 wavelengths, well, then they're constructively interfering. And so the way this can happen is through the slit experiment. It's actually a very important experiment, but all you need to know is this equation. And you have a coherent source coming in here, this part, and it hits these slits. And when it hits the slits, it spreads out. And those two waves now that are produced from those two slits spread out and they interfere. And depending on, you know, where we're at on the screen, well, we're going to have a bright or a dark, what we call fringe. That means a bright fringe means, well, we're getting constructive interference, and a dark fringe means we're getting destructive interference. And that's to do with the difference in the wavelength, the path difference. So at the bright spot, we'll have a path difference of 0 or 1 wavelength or 2 wavelength or 3 wavelength because they're constructively interfering. And at the dark fringes, well, we'll have destructive interference. So it'll be at half a wavelength, 1.5 wavelengths, right? And this equation here is relating the wavelength of the monochromatic light, which is just light of consistent wavelength, you know, hitting these slits or coming through these slits, the slit separation, the fringe separation, which is the distance between two adjacent fringes, so 2 bright spots or 2 dark spots, and the slit to screen distance, which is this distance here. So these are all related. And then diffraction gratings, well, it's the same thing, but we just have lots and lots of slits. And so we have these, you know, this n number here. I don't have a lot of time. This n number here is, you know, where a bright fringe is happening. So n equals 1 will be the center one, right? Obviously the center one will be constructive interference because the waves are just passing through in the coherent light, so they're going to be interfering constructively. And so we have a bright fringe here, a bright fringe here, a bright fringe here. Again, it's dependent on the path difference between the two waves when they exit the, well, in this case it'll be lots of waves, but when they exit the diffraction grating. And this is the equation for this. So it's relating the distance in the grating, so the distance between 2 separate grating lines. We'll consolidate this when we do questions. I've got 3 really good questions for you. The angle, which is the angle between, you know, the middle 0th and an nth of maximum. So this angle is, you know, if it was 1, then that would be this angle. If it was 2, then it would be this angle between 0 and 2. N is the maximum value, like what maximum we're interested in, and lambda is the wavelength. I found this video because proving it would take a little while. I don't want to make the video excessively long, but I found this video here. I want to give credit to this guy, but it's a really good proof. So if you want proofs for both of these equations, it's basically to do with the geometry of the situation and making certain assumptions. We can prove them, but you just need to recall them and understand how to use them. But if you'd like the proofs and to know where they come from, this is a really good video, so just click on that link. And finally, we got the idea of polarization. Again, let's recall that intensity is the power divided by area. That's its actual definition. And also recall that intensity is proportional to amplitude. You're also going to need to know, like I went through this in the last video about the electromagnetic waves. In particular, visible light. You just have to have a general idea that, okay, blue light is 500, red light is 700 nanometers. Just have a general idea. And plane polarization is basically, okay, when we unpolarized light through a Polaroid, well, what happens is it becomes plane polarized, meaning that all of the oscillations of that wave are now only acting in one plane. And then we have this Müller's law. This is basically relating the intensity of the incident, so this light coming into the Polaroid, and the intensity of the light coming out of the Polaroid. And the angle here is the angle between the transmission axis, which is basically the axis in which this thing is polarizing it out, and the plane of polarization of the incident light, so this light coming in. We'll do questions on this now, but those are the equations you need to understand. Maybe, I'm not sure my explanations were super brilliant there, but basically these 3 equations, 1, 2, and 3, these ones are the most important. You basically need to understand what these variables all mean. But we'll do questions and you'll get a better picture. Okay, so let's do first off a question to do with the double slit. So I'm remembering this equation here. So basically we have this scenario of a double slit, and obviously it's going to interfere and produce on a screen, it's going to produce bright and dark fringes to do with the constructive and destructive interference. And so we have this light with wavelength of this coming in here. We have a slit separation. We have the distance between the screen and the slit. And we have these central and dark fringes formed. The light waves from the two slits are coherent. What is meant by coherent? Well, coherent is just there's a constant phase difference between waves. They have a constant phase difference. For the two lights waves superposing at R, calculate the difference in their path lengths. So their path difference at R. So at this point here, their path difference is going to be 1.5 wavelengths. Why? Because it's a dark fringe. This fringe here would be at 0.5 wavelengths. This bright fringe here will be at 1 wavelength, and this here will be at 0. This is the path difference between these waves coming from each of these slits. Right? At this point here, they're perfectly destructively interfering, so therefore completely cancelling out. And that happens at half, 1.5, 2.5, these things. So this thing here, this dark fringe is at 1.5 lambda. So the path difference between the waves is 1.5 lambda, which is 1.5 times whatever the wavelength is, which is 660 nanometers. That's going to be what? 990? That's not. Look at it anyway. 990. Okay, so that times that's 990. Okay, their phase difference, well, simply it's a dark fringe, so their phase difference will be 180 degrees. 180 degrees, because when two waves are out of phase by 180 degrees, the coherent waves, well, they're going to be destructively interfering. I guess if you wanted to be more specific, you would say 1.5 times 180, but I mean, it's the same thing because it's a cycle, right? They're cycling. I guess you could say, what's that? 80 times. I mean, actually, no, fuck it. 180 is fine. Right, so they're out of phase by 180 degrees at these. Calculate the distance OQ. OQ is, yeah, so the distance OQ is the distance between the two central fringes. And so this, in terms of this equation, is x. So this is the distance between fringes, successive fringes. So we know that lambda equals ax over d. Well, a, so therefore if we rearrange this, we get lambda d over a. Okay, a is this distance between the two slits, and lambda is 660. So this is 660 nanometers, so 660. 660 times 10 to the negative 9 times d, which is this distance here, 1.8 meters, divided by a, which is this distance here. Remember, it has to be in meters, so it'd be 0.44 times 10 to the negative 3 in meters. And that, if you pull that in, you'll get about 0.44. 2.7%. 2.7 times 10 to the negative 3. Meters. Right, so that is the separation between fringes, successive fringes. That's what this x means. And obviously the distance, the separation between two bright fringes will be the same as the separation between two dark fringes. Right, 0 to a wavelength, half a wavelength to 1.5 wavelength. The intensity of light of an incident on the double slit is increased without changing the frequency. Describe the appearance of the fringes after this change, and similar to their appearance before the change. Okay, well, if we increase the intensity of the light, what's going to happen? Well, that means that the amplitude of the light is going to also increase, right? And if we increase the amplitude of the light, well, it's not going to do anything to the distance between these fringes, right? We're just increasing it up and down. You know, the amplitude, in terms of this equation, this doesn't relate to the amplitude. If we increase the intensity, the amplitude increases. Well, this doesn't relate to the amplitude. So the amplitude increasing does nothing to the distance between fringes. So, as you could say, distance between fringes stays the same. However, you know, the bright fringes will get brighter, right? It's increasing its amplitude. So therefore, when they're constructively interfering, if the amplitude is being increased, well, then it's going to be bigger and it's going to be more intense. So the bright fringes will be brighter. I guess you say the dark fringes will be unchanged. Why would the dark fringes be unchanged? Well, because they're constructively, destructively interfering. So at a dark fringe, we have a destructive interference between the waves. Right? And they're cancelling out. So it doesn't matter how big they both are. If the amplitudes are really big, but they're both really big by the same amount, well, then they're still going to cancel out to 0. I guess that's what they want. The light, it's important, like I looked at 3 marks, so I made 3 points. That's why I said, if it was 2 marks, I probably wouldn't have said that. But 3 marks, I guess I'll say that. The light of wavelength 660 is now replaced from blue. So this is why I said you should learn get an idea, because like blue light, if we look on this thing, where are you at? Like blue light here is 500. It's around 500. This is around 500 nanometers. And so now that we know that, so it's replaced with a wavelength. It's decreased the wavelength. So state and explain the change, if any, that must be made to the separation of the 2 slits so that the fringe separation of the screen stays the same for that of the 660. Well, let's look at this equation. So when it comes to this, when we're decreasing something and we want to know how something else is changing, we need to look at the equation. Okay, so we're decreasing this. We're decreasing the wavelength. And we want the fringe separation to stay the same. And obviously D will stay the same as well, right? Because the distance between the screen and the slits is going to be the same. So we want this thing here to remain constant. And so state and explain the change, if any, that must be made to the separation of the slits, which is this. So what's going to happen to this? Well, if we decrease this and want to keep this thing constant, this thing also has to decrease by the same amount, right? They're proportional to each other. So, say blue light is blue light wavelength is less, it's less than 660 nanometers, right? Because it's 500. So decreasing the wavelength and keeping this thing constant, we must also decrease the separation distance between slits, right? Okay, so you look at the equation. If we're decreasing the wavelength, we want to keep the slit, we want to get the fringe separation, obviously the distance between the screen and the slits. Well, then we also have to decrease the slit separation to keep this thing constant. Okay, now we'll do something on diffraction gratings. So, okay, diffraction grating, coherent. What is coherent? Well, it's just the same thing. It's producing coherent and produce an interference pattern. Well, coherence is constant. I just said this before. Constant phase difference between waves. Interference, or I guess it's the superposition of coherent sources. This is already a coherent source. So I guess it's just the combination of displacements of overlapping waves. Right? Interference means the waves are interfering, they're overlapping, and so the displacements are adding and cancelling and doing stuff like that. Interference is just, it's basically the same thing as superposition. It's just like, how are these waves interfering? A narrow beam of light laser is instantly normal to the diffraction grating as shown. Okay, so a diffraction grating is the same as two slits, but it's just like a bunch of slits, like heaps of them. And so now when it's come through, so if you look on my worksheet, I have diagrams. Now when the light comes through, well, it's diffracting a bunch of waves, but they're still interfering. And they'll interfere in a way to produce maximums and minimums on these screens. And so this is the equation that we're interested in now. E sine theta equals n lambda, second equation. And so they give us this 51 degrees, which is this. They give us this 51 degrees because of the second order, which is this. So this will be 2, this will be 51. And it also gives us the lines per unit length of the diffraction grating. So we get 6.7 times 10 to the 5 lines, grating lines per meter. So if we want the distance between an individual grating line, two individual grating lines, well, this is just going to be, you know, the distance would be 1 over 6.7 times 10 to the 5, right? That will be the distance, because this is 1 meter. This is in 1 meter. So if we want the distance between two adjacent ones, well, it will be 1 meter divided by how many we have. Okay, so to determine the wavelength, well, from this equation, the wavelength is just d sine theta over n. Right, d is this. Sine 51 degrees divided by n, which is 2. 1 divided by 6.7 E5. E5 times sine 51 divided by 2. So rounded to two significant figures, this is 5.8 times 10 to the 5.8 times 10 to the negative 7 meters. Right? It's just equations, man. It's just an equation for this situation. Just like before, this is just an equation. This is just an equation for the situation. With double slit, this is just an equation for the situation. It's like this is just an equation for the situation. Just understand what the equation is saying. and what these variables are. And then you can solve all these questions. It's not actually that hard. Like, these questions are just, they might look intimidating, but it's not that hard. Just understand the equation and what's going on, the phenomenon. You know, I tried to explain it. It's easier to just, I guess, look at diagrams. State and explain the change, if any, to the distance between second order maximum spots on the screen when the laser is replaced by a shorter wavelength. Okay, again, we'll just, you know, d sine theta equals n lambda. Okay, distance between second order. Maximums. Okay, so the distance between second order. If we decrease this, this is remaining second order, remaining the same. The diffraction grating is remaining the same. So if we decrease this, will we decrease the sine theta? Because sine theta, in this case, the theta will range from, you know, 0 to 90. This means when we decrease wavelength, well, we're decreasing sine theta. And if we decrease sine theta, well, if you look at the sine graph, you know, from 0 to 90, we decrease sine theta, well, we also decrease theta. The angle goes down too. This means the angle goes down. And if the angle goes down, well, the angle between this second order maximums, this angle, if this decreases, well, then the distance between this second order maximum spots on the screen will decrease. So decrease wavelength will decrease theta, thus decrease distance between second order max. Decrease this angle, well, these things are going to get closer. It's a short distance. Cool. Okay. Polarization. Not sure, did I explain it in the start? Polarization. Polarizing light. You have this unpolarized light. Light doing whatever it wants. It goes through a Polaroid, and then it's polarized to one plane. It's doing like this, crazy, and then polarized to one plane. Boom. So then you've got polarized light. So the meaning of polarization is just simply like oscillations. Oscillations are in a single plane. Right. Along like this plane also contains the wave propagation. It's also in the direction the wave is moving. State why light waves can be plane polarized but sound waves can't. This is because light waves, so only transverse waves can be polarized. Right? Sound is a longitudinal wave. Why can only transverse waves be polarized? Well, we're vibrating up and down. We're vibrating up and down, and when it hits the Polaroid, well, it's restricting it in the vertical direction. If we have like a pulse, that's a good way to think about it. Like if I had like a string and I was flicking it up and down, and then it went through a vertical slit. Well, no matter which way I flick it up and down, when it goes through the slit, it's going to be polarized, right? On the other side, we'll be doing this, and then it goes through the slit, and then it's doing this, right? If I do a pulse, like a longitudinal wave along the wave, well, no matter where I move it, because it's in this perpendicular direction to the propagation of the wave, well, the pulse is just going to go right through. So you can't polarize a longitudinal wave. Probably a terrible explanation. Look at the diagrams. Two polarized filters A and B are positioned so that they're okay. We have a filter A and a filter B. These questions, bro. Transmission axis, filter A, vertical. Okay, so this is filtering vertically. So the light is going to come out vertically. This is filtering horizontally. Unpolarized light of a single frequency is directed along the line XY from the source. X, okay. So the light from filter A is vertically plane polarized and has an intensity of I0. Okay, so this light, unpolarized light, is then polarized vertically. It then hits this thing and then is polarized again in another direction. So filter B is rotated from its starting position. The starting position was horizontal. As shown, after the rotation, the intensity of the light emerging from filter B is 1/4. Okay, so this is this. It's derived from thinking about the amplitudes. This intensity is related to amplitude squared. Proportional. Okay, so what are we doing? Okay, so this is the intensity of the light coming out. This is the polarized. This is I here, is this intensity of this light, and I0 is the intensity of this light. Okay, so the light emerging is this. So we're looking for this rotation, calculate the angle of rotation from B. Okay, so we just plug it into this. So the light coming out is the light going in. What's the angle? Well, these will cancel. You get, therefore, cos squared theta equals 1/4. Square root that. Be a half. Be plus or minus, but be a half. You can just make it positive because it's a cycle, so just repeat. cos inverse 1/2. What is this? What is this? Cos inverse of 1/2. I feel like I'm kind of not in the mood today. Sorry if I'm coming across a little. Maybe I'm a little cranky. 60 degrees. It's just a lot. It's a lot of info to teach in one thing, but I see no other way of setting this up. Okay, so theta is 60 degrees. So, okay, so what does this theta represent? So on the worksheet, I tell you exactly what it represents. So this is the angle between the transmission axis of the filter and the plane polarized of the incident light. So this angle is representing the angle between this and, whatever angle this is at. Now polarizing it out with that angle. All right. However, it begun horizontally. So, we have this angle. It's so hard to visualize it. It's so hard to draw. This angle is the angle between this light and then this light. Right? But that's not the angle of rotation because it started horizontally. So, this angle here is 60. The angle we want was this horizontal one, which is here. Just 30. Right, it starts horizontal, that's where it started. So that angle of rotation is 90 minus 60, which is 30 degrees. Or I guess you could say, I guess if it's asking for this way, I guess you say, you could also say 330 degrees, right? 330, because it'll go, all the way around. I guess you could say that also. But 30 is the same thing. Just say 30. Don't listen to me. Just say it's 30. I'm just trying to get you to see this thing about cycle. 180. This is like 360. This is cycling. Full cycle. It looks the same. Rotating something 30 degrees is also the same position as rotating it 330 degrees. If it was in a circle. 30 that way is also the same as 330 this way, because the whole thing is 360. I don't know. A microwave of intensity I0 and amplitude A0 meet intensity of a quarter. Okay, so we have a microwave, has this intensity, this amplitude, has the same frequency, meets another same frequency, and this one has intensity of this. Traveling the opposite direction. Microwaves are vertically plane, polarized, and superposed when they may explain without calculation why the waves cannot form a stationary wave with zero amplitude at its nodes. Oh, because the waves have different amplitude. They can't form a stationary wave because they have different amplitude. Because they have different amplitude. I feel like this video is getting so long, right? But you can't form a node. You know, we talked about this before in the previous video. You know, the node will form here, right, where these two waves cancel out. Well, if you've got one wave chilling up here and the other one chilling down here, well, they're not going to be able to cancel out, so you can't form a node. So, you know, can't have like perfect. Yeah, let's be formal. You can't. You be say can't. You be formal and write better than this. Can't have perfect. Just like me, perfect. Destructive. Destructive. I'm kind of destructive. Interference at nodal points. Right? It's impossible. They have different amplitudes. Determine in terms of A0 the maximum amplitude formed by the wave. Okay, well, I is proportional to A squared. So A0, like it says up there, has an amplitude. Is that amplitude, right? And so what would a quarter intensity have? Well, if I is proportional to A squared, what squared will give a quarter? Well, it means it'll have an amplitude of this. Half squared is a quarter. Right, so the maximum amplitude when these are added together. So A max, why is this 3 marks? I don't understand. A max is just going to be A0 plus a half. Yeah. So 1.5 A0. Right? What amplitude of wave is going to cause a quarter I0 if I0 has this amplitude? Well, it's going to be a half. A half squared is a quarter. A squared is proportional to I. 1.5. Right, there you go. A lot of info, but I covered it all. And honestly, look, just read through, look at these diagrams, read through. You just need to understand those 3 equations. That's it. Just understand them. You don't need to derive them. If you'd like deeper understanding, obviously you should go watch the video and look on the internet and go into like how they're derived. But you just need to understand what the variables are and how they relate to each other and what they're describing. And what they're describing isn't something that crazy. It's basically just interference. They're just describing interference. And at these points, they're constructively interference. And at the dark fringes, they're at the light fringes, they're constructively interfering, and at the dark fringes, they're destructively interfering. And I think I'm going crazy, but you know, so what? Right, so I'll talk more on waves. Let's talk more on waves. It's a pretty interesting phenomenon outside of physics. Your boy might be going a little mental, studying, talking about, teaching, and organizing waves for God knows how long now in this room, but I'll ride this wave. Like, let's think about this. I'll give you a pretty cool insight. There's many ways to think about a thing in terms of waves. We can zoom in and look like into the physical and the nature of waves and what I talked about before, which is a trippy thing anyway. To model reality, the best way to model it is through waves. Or we can zoom out and look at this from a higher perspective and see that the pattern of waves, this pattern is consistent across the universe. It's ups and downs, cycles, these kind of things. So it isn't just constrained to physics and studying physical nature. You know, when we look at history, this also happens. We look at, I don't know, culture and maybe even fashion and like even the universe as a whole. If we like zoom out from the entire universe and what's happened, like from the Big Bang from today, I mean, it's been like a cascade, a interference from a point outwards. Like it's a wave, man. There's so much going into this idea of waves. Even if you look at your own life, you go through the motion of sort of wave-like patterns. And I might be sounding crazy right now, but I don't care. Like you're going through these cycles of ups and downs, and even the feeling of time and how it progresses in your life. Maybe you'll feel this. You'll go through periods of where time feels very stretched, and then sometimes time goes very quickly. You know, it's this wave-like pattern to reality on very many levels. And it's super interesting. It's a super interesting phenomenon to just observe it and look at it. Because it's like, what the hell? Like, what the hell is going on with this wave thing? It seems so prominent in the universe. And I'm gonna cut myself off here because I'm gonna go on I feel like I could go on a ginormous rant, and maybe some people want to hear that, but the video is already getting so long. Well, I did go through a lot, but it's getting so long. Yeah, I'm just, waves, like, it's crazy. They're bloody everywhere. They're popping up everywhere. Anyway, I hope you enjoyed this. Hope you found it useful. Yeah, peace out. And if you feel like it, I guess, you could like the video if you want. But yeah, peace out.